Hi, everybody. My name is Jared Longfox from the University of Central Florida and the Department of Physics. I am one of the hosts of this AIAA Space Resources webinar series. This webinar series is an effort under the AIAA Space Resources Technical Committee's Education and Outreach Subcommittee, which I am one of the leads of. Today, we're fortunate enough to have Dr. Josh Racera from the Imperial College London, the Space and Terrestrial Resources Group within the Department of Earth Science and Engineering. Just for logistics, and I'll let Josh take it away in just a sec. For logistics, we will be doing a Q&A session at the end. There is a Q&A feature. If your Zoom is set up like mine, it's on that bottom ribbon. When you move your mouse, you should see it. There's a Q&A button, and you can type your questions in there, and we will get to them at the end. I should also mention that this is a recorded webinar, and I will be uploading the recording to YouTube within a day or so of the after we wrap up, so it'll be available there. Towards the end of the webinar, I'll paste links to the YouTube channel and our slide repository where we have the PDFs of slides that you can access from other speakers, and if Josh is willing and able to share his slides as well. So without further ado, I'll stop rambling and hand it over to you, Josh. Thank you for an exciting talk.
Great. Thank you so much, Jared. And thank you to the AIAA for having me present to you all today. So good morning to everybody in North America and good afternoon to my colleagues here in Europe. My name is Josh Racera, as Jared said, and today I'm going to be talking to you about getting to the good stuff, why we bother processing lunar minerals and why it matters. So before we begin and delve deeply into the topic of mining in space and why we mine in space and how we get to the good stuff, we have to talk about why we mine in general. Specifically, I'm going to start to set the scene by talking about why we mine on Earth. And one of the fundamental principles of being a human is that we consume things. And unfortunately, favorite sayings of my PhD supervisors, and it is actually extremely true. In the next, I think by 2040 or 2050 or something like that, we'll need to have mined almost as much copper as we've mined as a society for the last 10,000 years in order to meet much of the demand for the green energy transition. And a lot of people talk about the need for recycling, which is certainly important, and we can't ignore that as a stream for reusing and recycling materials, but it simply isn't enough to meet the demands that we are creating for ourselves. And so you can see in this chart here how the demand for resources on Earth has changed fundamentally over the last 100 or so years. So on the left-hand side, you can see in 1900, the annual extraction rate for material from the Earth from mining processes was around 7 billion tons. Fast forward again to 2005, and we're at 60 billion tons, so almost a factor of 10 increase in the total amount of material that we're mining. And then, fast forward again to 2050, and we're looking at potentially 140 billion tons per annum. And this is a huge increase in material that we have to take out of the Earth. And ultimately, it's being driven by increases in consumer patterns for things like technology, just increasing population, growing middle classes, where technology and things that used to be sort of not the preserve of, but tended to be unaffordable for a lot of people are becoming more and more affordable, thus driving the demand further for more and more resources. And so this is an interesting kind of bit of data from the United States Geological Survey, which talks about the demand for resources for an average infant born today. This might actually be for an average infant born 2 years ago, but it's probably roughly the same. And I'll call your attention just to the x-axis, which is on a logarithmic scale. Over the course of an infant's life born today, they will require 644 approximately 1,000 kilos of sand, stone, gravel, and cement to support all of the different activities that they will, go through in their lives. And that's, things like driving on roads, having a building to live in, that sort of thing. And you can see that these numbers are all high for even things like salt, iron ore, clays, aluminum, copper, lead, zinc. And this is just a small subset of all the different materials that we could possibly extract from the Earth that an individual infant born, say, in the United States today will actually require over the course of their life. Some of this we certainly can recycle, but a lot of it we can't, and much of it has to come from mining processes. Similarly, I mentioned before the drive for material consumption largely from the green energy transition. And in the right-hand side here, you can see a comparison of the amount of copper that's required for different vehicle types. So your sort of standard internal combustion engine will maybe require about 48 pounds or 25 odd kilos, 20 odd kilos of copper. A hybrid vehicle will require almost twice as much, but a battery electric vehicle requires almost 4 times as much copper as your average internal combustion engine. And this is sort of the complexity with the green energy transition is that, in order to move towards a fully electrified society, moving away from fossil fuels, the consumption of metals is going to increase remarkably, and copper is definitely one of those key drivers. On the left-hand side, you can see a periodic table of mobile phone elements. So, everybody or many people, I guess you could say, have mobile phones kicking around in their pockets or purses, and you rarely think about all the different bits that go into them, especially the metal components that comprise the various components within your phone. And you can see here on this periodic table, there's a huge variety of things that go into just a smartphone. And a lot of these things are probably elements that a lot of people have never heard about or even really considered being relevant to them at any point in time in their lives. They don't like lanthanum, cerium, europium, these sorts of things that you may have heard about in your high school chemistry class and then sort of forgot about for the rest of your days. These are actually becoming very important for a lot of the technology that we take for granted. And the way that we can get these materials is through mining. And this is how, we have to start going and producing more materials from the earth in order to meet the demand that we have today and that it's growing in the future as well. So this is why we mine. And so now if we think about, this is why we mine on Earth. Now, if we think about why we mine in space, the context is quite different. I mean, we don't have 8 billion people living on the moon. We don't have anybody living on the moon. But we still have this need to produce resources in space, more so as an enabling system, rather, or an enabling set of technologies and enabling resources, rather than something that is necessarily going to drive consumer demand. So the needs are different, but again, thinking back to the original question of if it can't be grown, it must be mined. If we look to places like the moon or to asteroids or to Mars, if we're looking for things like oxygen or water or metals for construction, those aren't things we're going to be able to grow on our own or grow at all. They're also not things that we'll be able to recycle in sufficient quantities in space. And so they're things that we are going to have to mine. So what is a resource? This is often the terminology that is associated with resources and metal production and mineral production are a bit confused, or they're a bit confusing, and they are also sort of, the confusion is added to by the sort of colloquial use of the word resources. So we're going to try to break it down a little bit to sort of clarify what we mean when we're talking about resources and the actual thing that we're talking about, which is actually known as reserves. But we'll get to that in a second. So when we think about resources, typically there's two categories. We think about renewable resources and non-renewable resources. And oftentimes, most people are familiar with this concept when we think about energy. So renewable energy are things like wind power, solar power, hydroelectric power, that sort of thing, where us consuming or generating power from these different sources isn't, by definition, eliminating or preventing the resupply of that resource in a reasonable amount of time. Non-renewable resources, things like fossil fuels, but also things like the mineral resources and metals that we extract from the earth. These are not renewable resources. I mean, perhaps they are renewable over geological timescales, but they're not renewable on a scale that we would actually be able to use them as a species. So once you mine out a vein of gold from the earth, for example, that's gone. You've mined it, it's done, that mine is finished. We can't expect that within our lifetimes, that mine is suddenly going to magic up more gold that we can mine out eventually again. Whereas if we build a wind farm in the middle of the desert or a solar farm in the middle of the desert, we can be fairly confident that between today and tomorrow, there will be more wind or more sun that will generate power for us. So what is actually a resource? So a resource is a naturally occurring material from which a valuable commodity can be extracted profitably. And all of these highlighted words are very important. So if anybody in the audience has ever attended Space Resources Roundtable at the Colorado School of Mines, Mike Duke, the founder of that conference, famously has said that there are 3 things that you need in order to have a space resource, but this is equally true for terrestrial resources as well. You must have a recoverable resource, you must have technology to recover it, and you need to have a customer. So by a recoverable resource, we mean something that we can actually get to. If we start talking about extracting gold from the Earth's mantle, that's not a resource. We can't recover it. There's no way for us to get there. There's no way for us to dig it out. I mean, technology aside, that's just getting to the resources is part of the problem. If you can't get to it, then it's out of the question. There's also, there's the technical aspects, but there's also the sort of legal aspects as well. I mean, if you've got, uh, this happens a lot in places all around the world. If you start digging and you find sort of human remains from past civilizations and that sort of thing, then you kind of have to stop. And so, you could have an ancient settlement on top of a perfect seam of gold, but that might not be legally allowable for you to actually dig through and extract those resources. So in that case, it's not so much a technical limitation, but more of a legal limitation. And this is something that certainly comes up quite often in space resources, but as an engineer, I am not qualified to talk about that. So we'll just leave the legality aspects of it aside for space for the time being. But yeah, so these are what we really need for in order for a resource to actually become something that we should even consider trying to go after. Because if we don't have a resource that we can get technology to get it and a customer to sell it to, then we don't really have anything. We just have shovelfuls of dirt. So that's kind of the how we actually view resources in more of an economic term and a practical term of what we can extract from the earth and how we can use it. But technically speaking, if we're talking to people like Jared who are geologists or geophysicists that are interested in this sort of distinctions between resources, reserves, and that sort of thing. So a resource is a concentration of naturally occurring solid, liquid, or gaseous material that presumably has some sort of value. And they exist in a form and quantity that is that enables the economic production of commodities from them, either currently or potentially in the future. So that means, anywhere that you can find something that may be valuable, but maybe you don't have the technology to do it, to extract it profitably now, or maybe the market conditions aren't suitable for it, it can still be classed as a resource, but you don't really necessarily have the means to extract it and to meet the sort of three criteria that we talked about before. So that's why we classify as a resource. A reserve, on the other hand, is the part of that resource that can be economically and legally extracted. So, if you look to the past, when explorers from Europe were going to the New World and they were trying to mine silver and gold, a lot of the silver and gold mines that they mined at the time, they were looking for seams of metal that they could see. So, you see something sparkly, you dig it up, and that's what you mine. If you don't see anything sparkly, you just stick it to your waste heap. The technology that they had at the time was pretty rudimentary, and so what they could see was what they would get. But as time goes on, technology improves. The waste piles that explorers would have been producing a couple of hundred years ago are now, by modern standards, extremely rich sources of copper and silver and gold that we can go back and reprocess and extract the material from. So that's the sort of difference between the resource and the reserve. What was considered a reserve for explorers 400 years ago would not be considered or would be considered still a reserve today. But what is considered a reserve today certainly would not have been considered a reserve at the time that there were explorers coming to North America. Mineral resources can become reserves and vice versa, and this switch back and forth is more so, or switch to becoming a reserve is more based on the technology advances in market prices. Going backwards towards becoming a resource again is largely driven by market price in and of itself. So I mean, in 2012 or the early part of the 2010s, there was a drop in global metal prices, and a lot of the grades that were, or the material concentrations that were at the time profitable or economic to actually extract were no longer worthy of extraction because the price that was being demanded by the market was just too low to make it worthwhile. And so that's when the reserve went back to being a resource, and companies would focus on mining out the bits that were just higher in concentration first. And like we said, legal, environmental, and economic constraints all need to be considered for this transition between resources and reserves. So all of this just to say, these are the different considerations that we have to think about when we talk about mining, and this is what we think about when we have to start thinking about space mining as well. So we think about, there's oftentimes in news articles very sensational titles and headlines about how NASA has identified asteroid made of platinum worth trillions of dollars, which is great, but we don't have really technology to recover that, and so it doesn't really matter. But then, you look at the moon where there's potentially lots and lots of water at the poles. And there's other metals that we could potentially use for construction, like iron or aluminum. These exist on the moon. We might have technology to extract them, but then the legal environment is a little bit confusing. And so we're not exactly sure if they are reserves or if they're resources. But these are all considerations that we have to put into any mining that we would ever want to do on Earth, but they're also equally important for any mining that we would want to do in space. So, how do we mine? This is an important question because I think most people are familiar with sort of the general concept of dig up dirt and then produce something from it. But there's actually a lot of consideration that goes into this, more so than that. And it's so I thought I'd take a step just to talk about how we actually go about doing mining and how this mining on Earth relates to mining in space as well. So before we actually dig anything up, we have to figure out where we're going to start digging. And so the way that we do this is by looking for places on the Earth where the geological processes that the Earth goes through has naturally increased the concentration of something that we're interested in comparison to the sort of global abundance of whatever that mineral or whatever that mineral or metal is. So for example, here I talk about gold. The average concentration of gold in the Earth's crust is 4 parts per billion. So if you were to just take a shovel and dig underneath where you're sitting right now, you probably will find something maybe around 4 parts per billionth of gold. Not really worth it for mining, but it might be there. The economic grade for gold, in order to actually make it profitable, is 1 gram per ton. So that's we've got to increase it by almost a factor of 1,000 in order to make it economical for us to warrant trying to dig it out of the earth. So this is the first step is figuring out where we actually need to go. But once we actually find out where we need to go and where these natural concentrations have actually been developed by the Earth over the millennia, we then have to go through what is called a sort of process flow sheet. And so here is a simplified one that we talk about often for space, but there's much more comprehensive and complex ones that we use for terrestrial mining. But this sort of cleanly distills everything down into 3 key steps. So first is excavation and haulage. So you have to, once you found where you're going to dig, you have to dig, and then you have to move it to wherever you're going to do the processing. So if you remember the picture that I showed at the very beginning, that's a huge mine in South America. You wouldn't actually do the processing where you're digging up because eventually you will dig underneath your processing facility. So you dig everything and you move it somewhere else where you can actually do all the downstream bits. So that's your kind of key first step is getting the stuff that you actually need to process that's been naturally concentrated by the earth. The next step is called beneficiation, and this is or mineral processing, and this is the area that my research primarily comes from. So in here, there's 3 kind of main areas. There's comminution, which is the grinding and crushing process that we have to go through in order to basically break any rocks that are connected together into individual pieces. So the idea here is that we want any individual grain or particle of rock to be only one type of thing. If you look at large kind of boulders and that sort of thing, they're usually comprised of a bunch of different colors or different types of rocks and that sort of thing. What we want to do is make sure that we grind everything down to a small enough size that those differences, each individual particle is its own thing and not a mixture of different things. And once we've done that, then we can have much more confidence that any of the processing that we're going to do on that, whether it's mineral enrichment or extraction for a metal or oxygen or something like that, is actually going to be only working on the thing that we care about as opposed to all the other things that could potentially be in that mixture. So we grind it down, we make it small, and then we sort everything by size. If we control the size, we tend to be able to have much better ability to control downstream enrichment processes, but also downstream extraction processes. We don't want to have anything that's too fine, and we don't want to have anything that's too coarse because it throws off how quickly our reactions can proceed and how effective our different technologies will ultimately be. And so anything that's too big will go back into the grinding circuit to make it smaller again. And anything that's too small will probably be classified as either waste or will go to a different processing circuit after that. Then we move on to the enrichment. So you've got all of your rock that's crushed down to a small size. It's been sorted into a discrete fraction of particle sizes. Now what you have to do is actually take out the thing you care about. So if you're mining for copper, for example, you're going to try to extract the say chalcopyrite as the mineral that you'd be after. So it's not the entire bit of the rock that you're looking for, but there's ways that we can concentrate just the copper bearing bits and then send those to a concentrate, which we can then extract the copper from downstream. So then, after beneficiation, we move on to extraction. The examples here are listed for more space mining concept or space mining commodities, so volatiles, oxygen, hydrogen, and metals, which would also be byproducts of this. But it's the same sort of concept on Earth, except usually we're not looking to get the gaseous forms. We're mostly looking for the metals that we would leave behind, whereas preliminary or initial sort of proving sort of test beds or pilot scale demonstrations for space resources will likely mostly be focused on the gases that are evolved, with the metals being more side products. So we have this whole flow sheet, and we have to go through each of these different stages in order to really get from just a sort of unconsolidated mass of rock into something that is an actual saleable commodity. And so this is the technology bit that we need to address in the sort of the three key aspects of having a resource. This is what we need in order to have the technology to extract something of value. Oftentimes people are very familiar with the extraction and haulage, excavation and haulage bit because it's kind of obvious. And the extraction bit is also, again, kind of obvious. I mean, you know that something has to be dug up and something has to be done to that rock in order to produce gold or copper or lead or whatever have you. But more often than not, people either forget or don't realize that there's this very important middle bit of beneficiation. And this is really how we can, this is the technology that we need that will really allow us to get to the good stuff. If we can't enrich the minerals that we're after specifically, then we're going to have a lot more of a difficult time doing the downstream extraction processes. And this is something that beneficiation is critical for terrestrial mining. If we didn't have this step, we wouldn't be able to economically produce anything. And I'll give you an example of how this works in the next couple of slides. Some key terms that I may have already said, but may end up coming, I will likely come back to in the next couple of slides. These are grade and recovery. So grade is the concentration or proportion of a valuable component within a feed or within an ore type, and it's usually expressed as a percentage or in grams per ton. This is what indicates the economic value of whatever you're digging up. The recovery is the percentage of that valuable component in the feed that's going into your process that you can ultimately extract and collect after it's gone through the processing stage. So recovery is more about characterizing the effectiveness of your separation process, whereas grade is more talking about the quality and value of the ore itself. So when we're talking about mineral processing, we often look at what are called grade recovery curves that you can see a sort of overly simplified example of on the right-hand side. In the upper, let me just get my little laser pointer. In the upper, so we won't actually separate out much of the original valuable component from the feed, but the quality of that concentrate is very high because the grade is almost pure. Whereas if we go to the other end of the spectrum, where we have almost 100% recovery and relatively low grade, this is essentially what we dig out of the ground. If we just dig and ship, the recovery is 100% because we haven't lost any of the material, but the grade will never be any better than what we dug up. So this is where mineral processing comes in, where we try to increase the grade whilst keeping the recovery as high as we possibly can. In a perfect world, we'd have 100% grade and 100% recovery, but that's not possible in most cases. So we just try to optimize this as best as possible to maximize our recovery and our grade without losing too much value of the ore that we've dug up, because of course there's a lot of cost and expense and complexity in getting these things out of the ground to begin with. And so we really have to make sure that whatever we're doing to process that ore to increase the grade and make it saleable, we don't lose too much of it in our processes as well. So let's talk about copper for a little while, because it's a pretty clear example of why beneficiation is very useful and why it sometimes gets forgotten about. So most metals that we mine exist as minerals. There are some exceptions to this. Of course, there is native copper, but generally that's not sort of the primary source of copper these days. Gold, some silver, platinum, root metals, those can exist in metallic forms, but more often than not, we do mine minerals instead. So for copper, chalcopyrite is one of the primary minerals that we mine. It's a sulfide mineral. You can see its chemical formula right here. Copper makes up only 34.5% of chalcopyrite. So if we have 1 ton of chalcopyrite, that means we have 345 kilos of copper within that ore itself. Great. So we can get out quite a bit of ore or quite a bit of copper from that ore. But the trouble is that this is not how we mine chalcopyrite. We don't mine a straight kind of large body of it. We mine a sulfide ore that contains some chalcopyrite. And so currently the economic grades of copper are about 0.5%. And so that basically boils down to 1 ton of copper ore mined results in only about 5 kilos of copper. So the amount of chalcopyrite that we actually have in any ore body at any point in time is actually quite low. Most of the other stuff that we're mining isn't copper bearing at all. It's just sort of waste rock. And so if we have to get from this 0.5% up to a saleable grade, which for a lot of smelters that are producing copper will be somewhere around 30 to 33%. We have to do a lot of work to get from this 0.5% copper up to something that's about 60 times as much. And so this image was shared with me a while ago by one of my PhD supervisors, Catherine Hadler. And this is an image from a South African artist called Dylan Marsh. And he's got an entire series of images on his website, which you can check out, or on his Instagram, where he places these, I guess, artificially rendered spheres of the material that a certain mine has been producing into that mine itself, to sort of show the relative scale of what is actually produced from what is actually dug up. And so this is from the Palabora mine in South Africa. And from the time it opened in 1956, it produced 4.1 million tons of copper. And so that ball that you see in the middle here is that 4.1 million tons relative to the size of the overall mine. And so you can see clearly there was a lot of work that had to go into taking all of this rock, much of it waste, and turning it into, by and large, a relatively small quantity of copper that would actually be used in any number of applications in the end. So it is not a trivial problem to go from these low concentrations to something that we actually can produce a saleable material from. And I think this is a really good example of kind of visualizing these differences in actual metal content versus the amount of material mined. So to sum up, basically we're trying to extract an ore from an ore body, and for copper this is a very low percentage. And then what we have to try to do is separate the valuable materials from the waste. And this is, once we've gone through all of these steps and have separated out the valuable materials from the waste, we then have something that's maybe around 30% copper, which is what our smelting partners or our customers are actually looking for. And so after we go through and go from this low concentration to this higher concentration, then this is the mineral processing step or beneficiation that we've been talking about. It's going from this 0.5% to the 30%. And ultimately from the metallurgical processing, we result in the essentially pure metals that we're after for any number of applications in the end. So really the challenge of mineral processing is making a high purity, or mineral processing and metallurgical processing is making a high purity metal from geological materials that by definition are highly variable. So we have to design processes that are flexible, that can handle various input feeds, while still being reliable to produce the levels of concentrates that we need in order to ensure that the economic component of our mining process is met. If we don't do things economically, then back to the original 3 questions, we no longer really have a resource that we can process. So this is the last slide at talking about terrestrial mining, and the point of this is to see what can we actually learn from terrestrial mining. And these are the kind of principles that will apply regardless of where we mine anywhere in the universe. So we need to consider and really understand the final product that we're trying to produce. That's critical. If we don't know what we're trying to get to, then we have a fundamental problem. And the raw material from which we are trying to extract it. So we have to know what we're starting with and where we're going, and then we have to know critically. The question that we have to ask ourselves is, how do we process this raw material to have confidence in meeting your production targets and getting from A to B? And so this is really what underpins the research that we do in our research group, is understanding how we can actually do this mineral processing in a way that gives us confidence in the outputs of our processes. So all that, now we can start talking about probably what most people are here to talk about, is space resources and beneficiation, in this case, particularly on the moon. So resources on the moon. The moon is It's our closest celestial neighbor. It's a very good place for us to potentially start doing space resource utilization or in situ resource utilization. The moon's about 260,000 miles away, 425,000 kilometers. It's got a relatively short communication delay compared to places like Mars. We've been to it before, which is helpful, and we know a reasonably good amount about well, we know some things about how the moon's formed. We know we have some points of data from return samples from the Apollo missions, from the Luna missions, and more recently from the Chang'e missions from China. Um, but there's so we have a good idea of what's available, and this is an interesting image that's been it's a false colored processing image to show the different composition of the lunar soil in various places. So the red bits are the lunar highlands. The blue and orange bits are volcanic lava flows from the lunar mare. Bluer areas indicate higher titanium content. Orange areas, lower titanium content. So you can see roughly kind of where things are on the moon. That being said, we do have some ground truth, but the total sum of the mass of material that we brought back to the Earth from the moon over the last half century or so is about 390 kilos, probably around these days. So under 400 kilos. If you were to take 400 kilos of dirt from anywhere, a rock anywhere on Earth, and were to go to a mining company like Rio Tinto or Anglo American or Teck or any of the companies that exist globally and say, hey, I've got 400 kilos of rock, I think we should mine here, you would be laughed out of their boardroom and no one would ever do anything because 400 kilos is basically nothing. And this is, I think, it's something that we as lunar scientists and people interested in space resources tend to often forget about that. If we are trying to talk seriously to people that do mining, if we say that our total amount of drill core equivalent is 400 kilos, no one's really going to take us seriously because those 400 kilos are basically what we're using to describe an entire planetary surface. Even if you're not trying to mine, if you took a few gallon buckets from Home Depot and you went around the world and got a few buckets of sand from various deserts and said, this describes the Earth, no one would really believe you because the differences between desert sand, even a single country can be quite substantial. Yet we're making these types of assumptions for the quality and the quantity of resources available on the moon. So that's not to say that they aren't there and that these maps aren't helpful. They certainly are. They guide where we need to go. So this is the sort of pre-concentration step that I was talking about before. If we're after things like ilmenite, which is a titanium-bearing mineral, then we're obviously going to want to head towards the blue areas. Landing somewhere red isn't going to get us anywhere quickly. If all the technology that we've built and developed is to isolate ilmenite, we land in the highlands, we're going to have a bad time. So this type of of orbital data sets, super useful, really gives us a lot of information to go off of. But ultimately, in the long run, we're going to need to do a lot more prospecting campaigns on surface for ground truth data points that will actually give us the higher level of confidence that we need to know what we're actually digging up. But it will all come in time. It's something that we will do eventually, but hasn't been done quite yet. So we know where we can go to find different things, but what are we actually dealing with? So, regular attendees of this webinar series will know the term regolith. It's the unconsolidated sort of rocky inorganic material that exists on the surface of the moon or other planetary bodies. What is it made out of? So, there's some examples that we've got here. So this is some soil from Apollo 11, or sorry, Jared, not soil. These are some rocks from Apollo 11 that were brought back by the astronauts. And so you can see there's a bunch of different things. There's basalt, some dust-covered basalt, impact melt breccias, agglutinates and orthosite feldspathic breccias. So, a lot of different rocks and mineral fragments. We have these glass beads that we think were formed from lunar volcanism early in the moon's history of evolution. We have these large-scale breccias, which are formed through impacts and other processes too, I believe. I'm not a geologist, so don't quote me on any of these geological sort of formation terms. You can ask Jared about that later if you've got burning questions. Agglutinates, which are formed by micrometeoroid impacts. They're glassy structures that are very vesicular and angular and sharp. They tend to exist in areas that have been exposed to space for a long period of time because sort of an indicator of how mature lunar soil is or how long it's been exposed to space is how many agglutinates that you have in any given sample. And then, of course, we've got the particle size distribution. And so the lunar regolith varies quite widely in its distribution of size. So about 25%, 23% to 25% falls below 20 micron, which is extremely fine. the average particle size is about 72 micron, and then the upper sort of 92% of the material falls below a millimeter. So anything above a millimeter is actually a relatively small proportion, at least of the material that was brought back and that was included in this analysis. So, that's to say that there's a reasonably wide kind of size distribution, but the size class is very, very fine already. So this is a kind of a benefit for space resources. I don't actually have to do much of that crushing and grinding comminution activity that I was talking about earlier because it's already pretty fine. So most of the activity that we have to do now is on size classification to make sure that we've got reasonably tight size distributions of particles, because not all processing technologies work equally well on all sizes of materials, depending on the forces that they're taking advantage of. And we also have to make sure that we aren't processing anything that's potentially not helpful for our process or our subsequent downstream processing. So if you've got a lot of material that's under 20 micron, that can get into seals, it can get into bearings. If you've got moving parts, the regolith itself is extremely abrasive, and it destroys seals and moving parts, bearings, as I've said. So we really want to make sure that we don't get this into other things. And if we've got humans involved, like astronauts going in and out of airlocks, we really want to make sure that the sub 20 micron fraction is minimized and not tracked in as much as possible, because that's the bit where we start having particles that are respirable. And that's where we start having some serious concerns about astronaut health. So at the end of the day, we have a very heterogeneous mixture of things, a wide variety of different particles and materials, and different size classes. And we have to deal with this in order to produce something that we can actually process. So we have this huge variety of stuff. Why do we now need to actually process it? Well, we've talked a little bit about this already, but in the lunar case, there's kind of two main reasons. So the first is that whenever we do anything in space, power and mass are really two of the big drivers for when we're trying to send anything into space. If it's really heavy or really power intensive, it will require a lot of other stuff that is also very heavy in order to generate that power. And in the case of lunar mineral processing or lunar mining and ISRU, that step that is very energy intensive and mass intensive as well is going to be the reactor that produces oxygen or metals. In comparison, the excavation equipment and the beneficiation equipment is all relatively low power and relatively low mass. So the idea here, and this plot that you see on the left-hand side, is that if we actually do beneficiation, this will result in a lower amount of material being sent to our reduction steps. That's the blue line here, which means that we can have a smaller reactor, which will require less power and will require less mass. But to compensate, we'll have to mine more of the lunar regolith, and we'll have to process that with the beneficiation step. But depending on the design of the systems and the architecture that's involved, increasing the mining rate and increasing the beneficiation throughput is probably going to be less problematic and less energy intensive and less mass intensive than having to have a much larger reactor that needs to be heated to 1,000+ degrees Celsius, depending on your process. The plot on the right-hand side here is talks about how then the other critical thing is actually being able to confidently produce the amount of oxygen that you need. And so this is from a study that my PhD supervisors and I did a little while ago, where we have a theoretical lunar mine with an annual demand for about 1,000 kilos of oxygen. And so we did a statistical estimation of the confidence of the mining and reduction feed rates that we would need using Monte Carlo in order to see kind of how much we would need to mine in order to have confidence, certain levels of confidence in our ability to produce that amount of material. And so essentially, if we want to have confidence, if we want to have 95% confidence that we are able to produce 1,000 kilos of oxygen per year, we're kind of ending up somewhere in this territory over here, mid 70s, 75-ish kilos per hour of excavation. If we don't care about meeting that target, if we're happy just to have like a 10% chance of meeting that excavation or meeting our 1,000 kilos a year, then we can operate down here in this sort of 27.5% kind of area. And now the interesting thing with this analysis is that previous studies that had been conducted in a way to kind of analyze the mass throughput needed in order to produce 1,000 kilos a year didn't really consider the variability of the regolith itself. And oftentimes, a lot of the rates that are quoted for excavation are quite a bit lower than the 70, 60, to 70 odd kilos per hour that we were discussing in our paper. And so this is where the beneficiation side of things becomes really important. If we need to have confidence, we need to be sure that we're excavating and processing and producing materials at a sufficiently high rate that we can be certain that we are going to have the throughput and the output that we're actually after. At this current point in time, and for initial sort of preliminary demonstration missions for ISRU, that's not really a huge concern. We're not really trying to keep anybody alive at this stage, but in the future, if we've got astronauts that are relying on the oxygen that's being produced, or water, or anything else, or even just for propellant to bring astronauts back up to the gateway or back to Earth, then having confidence in the output is going to be extremely important, and this is something that we definitely need to consider. But all of this is ultimately enabled by having robust beneficiation steps in the middle. So the last slide about Earth, and then we'll talk more about the moon again. So beneficiation on Earth, we do all these same sorts of things. We do sizing, we do flotation to do concentrations for things like chalcopyrite, or we do jigging and other activities to separate out gold. If you look at these three different images here, the kind of great unifier between them all is that they require vast amounts of water, liquid water. But on the moon, we have a few critical kind of environmental constraints that more or less prevent that. So there's no atmosphere on the moon, right? There's only a hard vacuum and a thin, dusty exosphere, which essentially precludes the existence of liquid water. There is water, of course, at the lunar poles. We're reasonably confident that there is. We're not exactly sure how much there is, but it's there. But in order to use it as a process fluid, as we do on Earth, we would have to mine the water, purify it, process it, compress it, and then use it as a process fluid, which sort of seems a bit ridiculous when there are other methods that we could use instead. So there's no atmosphere. There's extreme differences in temperature between the night and the day. The day-night cycle is extremely long. So when we see the full moon to the new moon cycle, that's one lunar day, and coupling those long lunar day-night periods with these extreme temperatures is not a trivial engineering challenge to overcome. The regolith, as I mentioned already, is extremely abrasive and difficult to work with. And the gravity is quite low. It's about a sixth of that of the Earth. And so, this isn't so much an issue for beneficiation. Actually, the lower gravity in some cases may be beneficial for us. But for things like excavation, it becomes more of a challenge. If you're trying to dig up soil in your garden, you've got Earth's 9.8 meters per second squared of acceleration behind you. On the moon, you've got only a sixth of that. So, if you've got to get that same shovel into the similar dirt, you're going to have a lot more difficulty doing so. And this is definitely a challenge for excavation technologies. So, the lunar environment is nothing but extreme, and this extreme nature really precludes the use of water as a process fluid. And so, for us as mineral processors looking at beneficiation, what we're really interested in is looking at dry processing methods. And there's really three ways that there's three different forces that we can take advantage of. So there's gravity or density separation that we can look at, magnetic separation, and electrostatics. So for my PhD and for many of my colleagues, we've primarily been focusing on electrostatics, largely because electrostatics it works very well in the lunar environment because there's, like we said, a vacuum, which sustains charge on particle surfaces very well. It's also less massive than magnetics. So, magnets are pretty heavy. They're mostly made of iron, and sending something heavy like that to the moon, as I said, has a mass penalty associated with it. So electrostatics is a really attractive option, but there's it's a bit fiddly and somewhat hard to deal with. But we also have been looking at gravity and density methods as well. And I'm going to talk a little bit about both gravity and electrostatic methods in the next couple of slides. So I've kind of broken up this last bit of the presentation into two parts. So there's the work that my group has done sort of at large, and then some of the work that I've been working on specifically over the last couple of years with various master students and researchers that I'm more excited about these days, and I'm going to talk a little bit more in detail on. So the first, we talk about classification, size classification, and this is some work from one of my colleagues who finished his PhD last year. And this is a method called the electrostatic traveling wave. And essentially what we have is a printed circuit board with three different electrodes embedded in it, and they're offset by 120 degrees. And when you turn on the system, the particles interact with the moving electrostatic field and shoot along in one direction or the other. And the easiest way to kind of show you that is with an example. And so these are some examples of this process in action. So this is using the white powder that you see on the printed circuit board is called ballatini. It's essentially spherical glass beads, and in this case, they're sized from 50 to 20 micron. And this is making sounds, but that's okay. So the difference between each of these different runs is that we've increased the frequency that the waves are moving at. So in the first video that I showed, it's at 150 hertz. The middle video is at, I think, 500 hertz. And then this one here is at 850 hertz. And you can see the particles, their motion behavior changes fundamentally from moving from to the right with the wave to moving against the wave direction in the high frequency condition. And so the reason why, this is neat to see in real life, and it's also neat to see in videos, but why do we even care about doing something like this? Well, it turns out that the frequency at which particles move forwards or backwards is actually dependent on their size. And so, there's a lot of information presented on this slide, but suffice it to say that the the particle size and the frequency that particles switch between moving forwards and backwards varies depending on their size. So if you have a mixture of particles, say the 130 to 30 to 50 micron particles and 220 to 280 micron particles, the frequency where the forward backward motion switches is quite different. And so if you have a mixture of these two size classes, if you pick a frequency that falls somewhere in between the two, where one particle moves reliably forward and the other particle moves reliably backwards, then you can actually do a fairly reasonable job of separating out particles by size using this method. And it doesn't require anything except putting some particles onto a printed circuit board and turning it on. So that's a very convenient electrostatic method to perform size classification with no moving parts, which is always great for space applications, and it's also very low power and low complexity. For mineral enrichment, this is some work for my PhD. So I was working on what's called triboelectrification and free fall separation. And so essentially, this is a very convoluted way of saying static electricity. So if you've ever taken a sweater out of the washing machine or the tumble dryer and it's got a sock stuck to it, that's been generated. The static electricity between the sock and the sweater has been generated by repeated contacts with the drum of the dryer and with the different fabric materials that are inside. We can take advantage of this exact same process and these properties for particle separation by trying to maximize the known particle or the known charge transfer between a particle and its environment versus the more random particle transfer between a particle and the wall, or between particles, different particles of different materials. And so for what I did was I developed a modeling method that would try to optimize the shape of this kind of twisty insert that you see in the upper right-hand side, and then try to see if having that twisty insert would markedly increase the separation performance of the system. And it turns out it does. So for this sort of binary mixture of two materials, we go from a reasonably decent separation without really having to do very much at all to a much higher quality separation simply by including this passive filter or this passive charging device. And so this is, again, another really nice application of electrostatics and a low complexity, reasonably highly efficient separation method that we could potentially use for enriching certain size or certain materials on the moon or other bodies in the solar system. So that's kind of what we've been doing a little bit at large. I mean, there's a lot of other electrostatic work, and we do some other areas of dry beneficiation as well. We looked at magnetics quite a bit in the last couple of years in a project with a terrestrial mining partner. But the size classification work that I've been working on with a number of students for the last couple of years, and I'm particularly excited about, is a process called the Brazil nut effect. And now this is, or the BNE, which will kind of be called in a lot of these slides. So many of you have probably experienced the BNE before in your life. If you've ever bought a box of mixed nuts or muesli, you'll have noticed that sometimes the large nuts seem to appear on the surface, and you don't really have a good explanation as to why. Well, this is actually a granular mechanics phenomenon, and there have been people that have done, in operando CT studies, as you can see here, and reconstructed it to show the motion of Brazil nuts as they rise to the surface of a mixed nut group. So the idea behind this essentially is that you apply vibrations, vertical vibrations, to a mixture of materials, and through convection and void filling processes, the larger particles make their way to the top. So with my students, we looked at a couple of different effects. We've been looking at the effects of the material itself. We've been looking at vessel effects, so the shape, and also the gravitational effects. And as I know, I'm running out a little bit out of time, so I'm going to try to get through this somewhat quickly. So some of the key findings. So the first thing we looked at was the compositional effects. And to study this, we looked at two simulants produced by Space Resource Technologies in Florida. We looked at Lunar Highland Simulant 1 and Lunar Mare Simulant 1. LHS1 is mineralogically far more straightforward. It's less complex than LMS1. And what we ultimately see is that the LHS1 does a really good job of separating. You can see a very clear distinction between a coarse particle cut at the top and a fine particle cut at the bottom, whereas the more mineralogically complex LMS sample has a coarser bit at the top, a fine sort of intermediate layer in the middle, and then a sort of unconsolidated mixed bit at the bottom. And so basically what we find is that as the material complexity increases, the increased likelihood, we increase the likelihood of forming this sort of packed intermediate jammed layer, which prevents the ascension of large particles and the descension of the fines. And so this is an interesting result that we didn't really expect. But it suggests that if we were to do this on the moon, that we could have better results in the highlands than we would necessarily in the mare. We also looked at the impact of just purchasing the dust fraction, so anything that's under kind of 20 microns. And to use this, we used the dust cuts of the LHS and LMS simulants, and they worked very poorly. You can see here, basically, as they started shaking, they started to form these statically charged agglomerates and turned into these large lumps, and then created, once again, a sort of packed middle layer here. And that prevented, A, the large lumps from ascending, but also from any real kind of performance of separation actually occurring. And this is because the fine particles have a very high surface area to volume ratio, which increases remarkably the interparticle forces. And that really is what causes these agglomerates to form, but also causes the packing structure that we see kind of in the middle range here as well. Finally, this one student was kind of working on all these three projects simultaneously. He looked at the impact of a particle shape. And so what happens if we have ideal, perfectly circular or perfectly spherical particles compared to introducing those agglutinate, those angular, glassy particles that I talked about earlier into a real simulant? And what we found is that perfectly spherical particles do a very nice job of separating. As you can see here, all the big ones rose to the surface, and then we've got the finer ones all at the bottom. But as soon as we introduce 25% by mass of the agglutinate particles into the LMS and LHS1, it totally messes up the entire separation process. So before the LHS1, which was on the top before, is now on the bottom, it had the really nice kind of bimodal distribution with the coarse on top and the fines on the bottom. That's now gone. We have this sort of swoopy, kind of turbid distribution here. And for the coarse particle, or for the LMS one, it's, again, a poor distribution of particles. We've got this sort of central fountain of particles, of fine particles, and then the coarse particles make their way to the outside. So this interlocking behavior from the agglutinates really disrupts the convection cells, and it prevents the effective void filling from occurring, which really disrupts the Brazil nut effect and reduces the efficiency. So again, another important finding is that if we were to try to do this on the moon, it probably would be better to try to do so in areas where the soil is less mature, or if we have to do it in a more kind of exposed area on the moon, then we probably should dig away the first few centimeters or so to get rid of the agglutinates as much as possible, and then deal with the subsurface that is probably, or hopefully, a little bit less agglutinate rich. The next thing we looked at was the shape of the container itself. So we looked at a triangular cross-section, a square cross-section, and a circular cross-section to see if that had any impact on the separation performance, and also whether or not we included, again, this sort of sub 90 micron fine part into the material. And what we found is that the circular and rectangular or square cross sections demonstrated the Brazil nut effect as we would expect. Large particles move to the top, but in the triangular vessel, it stopped working. And in some cases, we had the reverse Brazil nut effect happen, where the large particles sank to the bottom and the fine particles rise to the surface. And so this is something we still are trying to unpack exactly why what the impact of the geometry is. If it's the sort of interruption of the convection cells that does it, and if that's a function of the angle. Like if we had a much larger triangular shape, would that have minimized this impact, or is it just is it something else entirely? So we're still working on figuring out exactly why this is happening. But something else we did notice is that the presence of the fine materials, the sub 90 micron particles, really has a strong impact on modifying the geomechanical properties of the sample. Even though these are ideal spheres, as soon as we included the sub 90 micron material, we started getting this hump or bulging distribution of particles at the surface of the sample. And when that 90 micron, sub 90 micron fraction was gone, these samples resulted in just sort of, they were flat at the top after the experiments were finished. And so the interparticle friction that's increased because of the presence of the fine particles is what leads to this bulging behavior. And so there's really there's so many different variables that impact this, but the presence of fines is definitely one of them. So finally, the last thing we did was look to see how well would this work on the moon. And so one of my other students looked at varying using discrete element method modeling. He looked at modeling an equivalent mixture of 1 part big to 1 part small particles and 1 part big to 2 part small particles with sample sizes of about 2 grams. So I mean, this is pretty tiny, but it's easy enough to model. So that's why we did these small size classes. And he varied the frequency and amplitude and the sample mixture ratios, as I've said. And ultimately, what he found is actually that on the moon, this Brazilian effect might work better. We can't often say that about things because usually as soon as we start going to the moon, stuff becomes a lot more difficult. But because of the difference in the gravity, we find that the separation happens more quickly and it happens more strongly. And we don't necessarily experience this at all when we do simulations under terrestrial gravity. So this is supporting the notion that the Brazilian effect might actually be a really good way of separating particles by size in the moon, with the caveat that all of the other experimental work that I just showed is kind of dealt with first. So shape of the geometry of the container, the presence of the fine particles, so there's a lot of things that we have to decouple and figure out the exact contributions of. But it's an extremely interesting area of research, and it's something that we've been working on slowly over the last couple of years, but hopefully we'll be kind of doing more of in the near future. It's something that I'm very interested in and seeing how we can develop this further for other applications as well. So in summary, terrestrial mining and neural processing provides us with a lot of good examples for techniques and technologies that we can draw inspiration from, but not really technology from for lunar resource extraction. The moon provides really strong challenges and significant challenges for implementing common terrestrial mineral processing methods directly. So, like I said, we can't really produce water just for a process fluid. So we have to start thinking a little bit more creatively. We have to take advantage of different forces, so magnetics, electrostatics, gravity, in order to prepare the feedstocks that we need for oxygen and metal extraction. And for me, the Brazilian effect is a really exciting phenomenon that we think will show some potential for lunar ISRU applications moving forwards. And so with that, I'd like to say thank you once again to Jared and the AIAA for having me. I'm sorry that this was a bit longer than I was planning for it to be, but if there's time, I'll take some questions now, but otherwise, please feel free to reach out to me. My email's on the page here. I'm more than happy to answer any questions you've got. Thank you.
Perfect. I think we do have time for some questions, but first, Josh, thank you for the excellent talk.
You're very welcome.
And before I get to the first question, I just punched in the chat links that I promised earlier to the YouTube channel where this recording will be able to be found in a day or two, as well as the slide repository where the slides from the webinars are available with a free account. You do need to make an AIAA account. You do not need to pay membership dues to access this. It's available to the public. So the first question comes from Donald Barker, which is not a question, but a suggested reading, which I'm going to post a link to in the chat because the paper certainly does look interesting. If it lets me copy and paste from there we go. So in the chat, there is a link to the paper Don suggested regarding lunar and offers resource drivers estimations and so on. Oh, and Don, it's one of your papers. This looks cool. Thank you. Anyhow, answer live, done. The other one in the Q&A, it comes from Jasper Julian, who asked, are any PGMs or platinum group metals on the moon that are worth returning to Earth?
That's a good question. I don't know the answer to that. My gut feeling is no, but I mean I don't think I've ever seen anything that talks about PGMs on the moon. But yeah, I don't think so. That's probably more of a question for you, Jared, than me.
The answer is generally, I mean, it depends on how scarce the resource becomes here on Earth. Generally, no. The launch costs just to get and transportation costs to get back to Earth are going to be excessive for any PGMs or anything like that. But that said, there was a really interesting presentation. I believe it was by the United States Geologic Survey, USGS, at Space Resources Roundtable this year. Maybe it wasn't them, but there was an analysis of how much the rare earth elements and PGMs were in the lunar regolith, and the upper limit for that seemed to be about on par with what we see here on Earth for RE enrichment. So it's probably not an economically viable thing, is what I say. If their upper limit on the moon is kind of our standard, that's not a great sign for returning to Earth. Still really useful on the moon, but we've got better here, kind of deal. So thank you for that question, Jasper. The next one comes from Sean Mitra. Do you see any dust mitigation benefits from your electrostatic approach?
Oh yeah, for sure. This is actually like that's one of the huge sort of areas that we drew inspiration from for that work was from dust mitigation. And so, a lot of the work that's been published in the literature previously has been more in that type of area. Or in more conveyance rather than in separation. And so my colleague Yue, who did the work, he was one of the, I think, the first person to look at actually using the differences in frequency to do the separation. But there's been papers for the last probably 20 years or so about electrostatic traveling waves, but also electrodynamic screens. There's been a lot of work at Kennedy Space Center on electrodynamic screens, and there's a lot of very cool work that's being done there for dust mitigation for seals in habitat environments. But also some of the other applications for this are potentially for solar panels in solar farms and deserts. Instead of having mechanical cleaning property or cleaning processes, if you embed not necessarily even traveling waves, but just moving electrostatic fields into the circuit or into the glass that covers your solar cells, you can kind of have a sort of self-powering electrostatic cleaning approach for removing sand or dust from solar cells in the desert. So yes, this is it's hugely practical for dust applications, and it's definitely a really interesting area of work. But it's not something that we've specifically looked on in our work because we're mostly interested in the resources and beneficiation side of things.
Makes sense. I don't see another in the Q&A, and we are already a little bit over, so I'm going to call it there. But as Josh said, his email address is just up on the slide, and if you don't have that written down, lose it, whatever, feel free to reach out to me and I can connect you. I believe most of you have my contact info through one way or another. So with that, again, Josh, thank you so much for your time and for this interesting and unique talk.
Well, thank you for having me.
It's a really fundamental technology you guys are developing, and I'm really happy to see it coming forward. This has a lot of promise. So cheers to
Thanks.
you and your team.
Likewise.
Um, with that, everybody, I hope you have a great rest of your Tuesday. Stay tuned for next month's webinar announcement in at the beginning of October, and reach out if you need anything. Again, I'm Jared Longfox from the University of Central Florida on behalf of the AIAA Space Resources Technical Committee. Josh, thanks again. Everybody, I look forward to seeing you soon. Bye.
Thank you. Bye bye.